In computer science, when we design an algorithm, we care about how much resources it uses. The two main resources in computer science are time and space. Among these, time is usually considered more important because one of the many reasons is that it directly affects the practical usability and performance of algorithms. The time complexity of an algorithm is defined in terms of the size of its input. It describes how the running time of the algorithm grows as the input size increases. Instead of measuring actual time in seconds, we usually express it as the number of steps the algorithm takes for a given input. When we solve a problem with an algorithm, we feed it specific values called parameters. When we say an algorithm solves the problem, the algorithm is capable of giving a solution for all possible instances of the problem. Parameters with their specific values describe an instance. Therefore, the amount of input data needed to describe an instance is the size of the instance. We count the steps in the worst case scenario because we want to be sure the algorithm always performs reasonably well. Let's take an example of searching. We have six integer elements and we want to check if 6 is present. 6 can be anywhere, right? If 6 is the first number, we find it in one step. If it is the second, it takes two steps, and so on. But if 6 is the last or not present, we need 6 steps. This specific case is the worst case, right? Because we need to follow the maximum number of steps in this case. So, if there are n elements, we may need n steps in the worst case in linear search. If we observe the worst case scenario, time or number of steps grows linearly with input size, right? We usually express time complexity with big O notation. Big O notation ignores constants and lower order terms because when n is big, the biggest term dominates. If the number of steps taken by an algorithm is function f of n and there is a function c times g of n that's always greater than or equal to f of n for large enough n, we say the time complexity is big O of g of n or order of g of n. Big O notation tells us the upper bound of the algorithm's running time, so we know how much time it will take as the input gets bigger. We are interested in the algorithm which has the least time complexity. In other words, we are interested in the fastest algorithm. Let us say for a problem, two algorithms exist with time complexity order of n square and order of n cube. We can say an algorithm with order of n square is more efficient compared to other one. But we are not interested in this efficiency. We are interested in knowing whether any algorithm with polynomial time complexity exists for the problem. We say that for a problem, if there exists a polynomial time complexity algorithm, then the algorithm is efficient. And if the algorithm has exponential time complexity or worse, then the algorithm is not efficient or intractable. In computer science, an intractable problem is a problem that cannot be solved efficiently, or we can say no known algorithm can solve it in a reasonable amount of time for large inputs. For small inputs, they may run fine. If we consider the case of traveling salesman problem, if there are four cities, there are three possible routes that we have to explore to find the route with the lowest cost, which is easy to compute. For 10 cities, possible routes are 1,81,440. This number is still manageable. However, for 20 cities, the possible routes are a huge number, right? The number of possible routes in the case of n cities is n minus 1 factorial by 2. Therefore, we can say time complexity of the problem is order of n factorial. This is worse than exponential. Even the fastest computers can't go through all possibilities when n is large. Let us see the categorization of intractable problems. We can categorize intractable problems into two categories: provably intractable problems and not provably but believed to be intractable problems. Undecidable problems are provably intractable problems. Formal proofs exist stating that no algorithm can be given to solve the problem. Furthermore, one more category of provably intractable problems is non deterministically intractable. Non-deterministically, this means there is a theoretical model of a computer that can explore an unbounded number of computational paths at once to find the solution. Non-deterministically intractable problems are those problems that cannot be solved in polynomial time even when they are solved by a non-deterministic theoretical computer. Proofs exist for these problems too. So, undecidable problems and non-deterministically intractable problems are provably intractable problems. However, we are mainly interested in the second category, problems that are believed to be intractable but no one has proven them yet. These problems can be solved by a non-deterministic machine in polynomial time, but we don't have any proof that a regular computer can't solve them quickly. Since no formal proof exists, mathematicians and computer scientists handle these problems in two ways. They try to design a proof to prove that the problem is intractable. The other way is to find the relationship between problems in terms of their computational difficulty. We are interested in this second approach. The concept of reducibility is used to define the relationship between the two problems. Suppose one problem can be reduced to another problem. In that case, the solution to the second problem can be helpful in designing the solution for the first problem. We are going to learn about reducibility in the last part of this series. To study intractability or difficulty of computational problems, we define a complexity class where we group problems that can be solved using a specific amount of resources. The resource we are talking about is time. In this video, we explore the concept of time complexity and what makes a problem tractable or intractable. This foundation will help us better understand the P and NP classes in the upcoming videos. In the next episode, we will dive into encoding and explore computational models. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.